independently by the listeners. Yes. So it is a lecture, yes. 1 second, I need to, for that lecture, I need to open the, open a presentation. And it is here. 1 second, I need to look at my screen. My screen needs magnification. Let me check if, no, this not. Oh, yes. No, I will switch it off. Because when I switch it on, I cannot see the letters. I need a microscope. And you did not provide me a microscope, so I need to switch it on. So we return to the slides which were explained a little by Professor Katyar. Right? 1 second. Yes. Oh, what happens? Okay. It works. So we looked at zippers. Yes. Considered how to build zippers of different signature, right? And one very important fact that zipper creates a curve, which is a Peano curve passing through the attractor of a zipper. Yes? Why? If you have a zipper, then we can parameterize it. We can make a natural parametrization, or it is a structural parameterization of a zipper. You see, suppose you have some kind of a zipper, for example, this one. Right? And we can make an elementary zipper, whose vertices are situated on a line. Yes? So it will be S1, S2, S3, and this will be T1, T2, T3. And we can make a, how to call it, a morphisms of two zippers, yes? So which will be compatible with this system and with this system too. So we have a map F, and this map is satisfies the following equation. F of Ti of x is equal to Ti or Si of f of x. So if I have a point and I have its image, right? And if I applied some maps, maybe T1, this point goes here to T1 of x, and the image of T1 of x will be S1 of f of x. So this mapping is easy to construct, because it's also this mapping may be considered as a special case of fractal interpolation functions. Yes, because it's a function with values in the plane. Yes, so it's and this equation is the same as the equation of fractal interpolation function. So when a point travels along this interval, its image will travel along the attractor of this zipper. So it will be a piano curve running through the attractor. It will be a piano curve running through the attractor. So when Sierpinski, does it work? Oh. When Sierpinski projected his Sierpinski carpet or Sierpinski gasket, so he made such a piano curve. What? And his intention was to make a curve which has double points everywhere. You see that this branch of this curve and this branch so meet at that point, and this meeting point repeats everywhere. So the name of this paper, an example of a curve which has ramification point everywhere. Okay. So zippers, but you would ask me, why the attractor of a zipper is connected? But you see the zipper has one intersection property. Yes, because each copy of a zipper has a non-empty intersection with the next copy. Therefore, the intersection graph is connected, and if intersection graph is connected, the attractor is too connected. Yes, so zippers are just self-similar curves which may have double points. Okay. And this map, which sends elementary zipper to this zipper, is called a structural parameterization. Structural parameterization of the zipper per K of S, where S is the system S, S1, S3, Sm minus 1. Yes. So when we consider the relation between the zipper and elementary zipper and its parameterization, then we see that it will be Hölder continuous. Yes. And its Hölder constant will be minimum of relation between logarithm of Qi and logarithm of coefficients for Ti. Yes. In that sense, it is better to make these contraction ratios similar to each other. Yes. In that case, this the ratios of logarithms will be the same, and it will give us the same Helder constant everywhere. Okay. So what is interesting is how to recognize when the attractor of a zipper is a Jordan arc. Yes? You saw that some attractors are Jordan arcs and some are not. What happens? So if the attractor of a zipper is a Jordan arc, then its copies do not intersect, with the only exclusion that they intersect at their common endpoints. Yes? And again, if the copy intersect only at these common endpoints, then the attractor of a zipper will be a Jordan arc. So here is the theorem. Suppose we have a zipper with vertices x0, xm. No matter in which metric space it is. You have questions? Yes, I welcome all the questions. If there are no questions, it is not good. And if for any ij, so it will have several copies, ki, kj. So if I and j, if j minus I is more than 1, then this copy do not intersect. And at the same time, if j is equal to I plus 1, they should intersect in a unique point, which is the common endpoint of these two copies. And in this case, the structural parameterization will be a homeomorphism between a line and a Jordan arc. Will be homeomorphism between a line and a Jordan arc. So there are two cases when these two zippers are Jordan. So when we consider this, so you have a zipper and you have a common endpoint of two arcs. So this will be S1 of gamma, and this will be S2 of gamma. S2 of gamma. And this will be 0 and 1. So there are two cases. If you have here, for example, S1 of 1 is equal to S2 of 1, then we have two similar arcs, yes? And one arc is obtained from the other by some kind of a similarity, yes? And these arcs act as loxodromes. They are spirals, yes? So if you have two spirals, they can meet each other in two ways. First, if the angles of inclinations of spirals are the same, yes, then they will have one point in intersection. But if the angles of inclinations of two spirals are different, then they will intersect each other in infinite number of points. In this case, it is good to look at this situation from the point of complex analysis. So in complex analysis, if you have S of z equal to q e to the power I alpha z, yes, then, so if you take some points and you consider the images s to the power of n of some initial point z0, yes, z0, then this point will lie on a logarithmic spiral, yes? But in reality, the curve is different, yes? Yes. But if we take a logarithmic transformation to this picture, then this curve is transformed to a, so you know that logarithm is a multivariate function. And its values differ by 2k pi. Yes. So if I take the logarithm of z0, then I will get logarithm z0, logarithm z0, z0 plus 2 pi, 2i pi, yes. Then we'll have logarithm z0 plus 4 I pi, etc. Yes, we'll get a sequence, infinite sequence of these values. And if I take a logarithm of q e to the power a alpha of z0, then I will get, so let us take this logarithm. Logarithm of q e to the power of a alpha z0, it will be equal to logarithm q, right, plus I alpha plus logarithm z0, yes? So this similarity transformation, after taking a logarithm, becomes a translation, right? It will be a translation of the whole plane. So when we take this logarithm, this point is translated, it will be z logarithm z0 plus logarithm q plus I alpha. And there will be an arc connecting these 2 points. And instead of having one arc, we'll have a family of parallel arcs, right? Oh, sorry, don't you feel tired of complex analysis? Is it good that I explain to you these things? I need a feedback if you may be dissatisfied or you have some questions, then please ask me your questions. Okay? And if we repeat this S, then we'll get the parallel copy of this arc, and we'll get a family of parallel curves. Right? A family of parallel curves which are invariant with respect to this translation. Plus logarithm q plus I alpha. Yes? Logarithm, since q is less than 1, this is translation to the left. Yes, but I alpha can be quite different. Yes, so this will be parallel lines. But we have a meeting point of 2 copies, yes? And for the second copy we have another transformation. So this is the logarithm q1 plus a alpha, q1 plus a alpha, and the other will be plus logarithm q2 plus a, well, plus a alpha 2, right? So we'll have another family of parallel periodic curves. But for these periodic curves, we can define the angle of the inclination, and angle will be the arctangent of logarithm alpha divided by logarithm q, right? Yes. And if these angle coefficients are equal, then we'll have a chance that these parallel lines do not intersect. But if the angles are different, they will intersect each other infinite number of times. Yes. So this picture can be seen on your zippers of signature 00 when you make some kind of an angle. Yes. So do you have such zippers on your pictures? So notes. Yes, but I need to see where is the meeting point of one copy and the other. So when you have signature 00, then you'll have such intersections of spirals at any. Yes, it is visible, but the problem is, so it is 0, it is 1, and this is point AB. It is somewhere, yes? Okay. Can you look at it? Did you look at your... no, this is signature 1. You need signature 00. Yes, signature 0. Yes, you see? Oh, very good picture. So you can magnify this part. You can magnify. Oh, not. Return back. Okay. And make some. I need you return back. Yes, this button. And then you have this meeting point. It is here, and make a symmetric rectangle about this point. Okay, that's good. So you see this. You see how these two spirals intersect each other infinite number of times. Yes. Yes. When yellow and white meet. So, and you have very good pictures. Because different, if a person is good, then his or her pictures are very good, and he cannot spoil it even he wants. You have this? Oh no, you have here some problems, some very special problems. But it is. You need to you need to change the parameters A and B. Oh, sorry. So if you change the parameters A and B, whereas parameters again, source, controls, yes, controls. You see, they are very small. Let me make it greater. very strange. A must be 1/2. Something like 1/2. Okay. And B maybe whatever you like. Maybe let's make it smaller. Yes, okay. And then you need to make it this way. And look at this picture. Oh. Yes, I cannot, so you need to, yes. So, 1 second, if you have one colored picture, please press the button rendering, view rendering. So there is a view, and then rendering, and yes, press depth. Change the depth. Then the copies will be view. Oh. So what happens? Yes. Okay.
Changes the depth.
No, but you need to see the attractor. Note, it is K00, yes. It's always a secret. What name? No, I mean, I don't mean that. I mean the parameters, controls. So A is good, but B, let us make B greater. Maybe we'll make B greater, and now we have these two spirals, but this, okay, let it be so. So we can look here. Oh, no, sorry. Tools, zoom box. Oh, tools. Okay. So there are spirals and spirals and spirals, yes? Okay, and what? Not working, it's a very special problem. Okay, so now you saw this infinite number of intersections, but in the case when these ratios are equal, then everything is okay. Now let us continue. So this is just a picture of this logarithmic transformation. There was a very good program called FractRacer, and I had a dream of applying it, which can apply different transformation to different fractals. I used it till 2013, but then IFS style appeared, which is faster, and also I changed from Windows to macOS, but FractRacer works on the Windows, so maybe we can discuss if you have Windows, and if you wish to install it, we may discuss this FractRacer program, because it makes what? The name. This program was built by the same person, by Dmitry Mikhontsev, FractRacer. But now I don't know. He had, maybe it can be available from fractracer.com, but he left it. He supposed that it can be used for building different landscapes for computer games, but this dream was not realized. So So, but this fractracer, I could take a maybe, for example, Menger sponge, yes, and from this Menger sponges, I made a torus, and I could rotate the torus around this axis. So I have video of such Menger sponge. I can show you this picture. So it allowed to take a fractal and cut it by surface and made this surface cut of fractals. So it is very interesting. For example, I took Menger sponge and cut it by a ball. So I got Menger ball. So it looks so many unusual features of fractals can be uncovered using this program. But so we can make an attempt to install it, but I need Windows on my laptop, and this is not easy to realize. So when this zipper has alternate signatures, yes, then this parameter matching condition is satisfied automatically. So there is some domain of parameters for zippers with alternate signatures, yes, in which all the attractors are Jordan arcs. So this is very good. So when you look at the picture, when you have this one, then you have this one and this one, and change parameters, then you will discover that in this case almost all attractors are Jordan arcs. Almost all attractors are Jordan arcs. Yes, maybe I can show you the movie of the type if I succeed this. When we have a break, can you explain at which time we need to make a break?
So it's already break time.
It's already break.
It's 4 minutes. After 4 minutes we can have.
After 4 minutes we make a break. Oh, that's very good. Then I will find you that nice picture which shows that Z all. Z. Oh, sorry, I to find everything I need to all. Okay, I will show you this picture after the break, and now I continue my talk. Where is it? It is here, I suppose. Okay. So the problem is, what is a multi-zipper? Multi-zipper is the same as the zipper, but if we have several polygonal lines, and we begin to map. So we have, for example, we have two attractors, K1 and K2. Yes. and one is maybe is represented by such a zipper and such a polygonal line, and this is represented maybe by that polygonal line, right? Yes. But we may, by some arbitrary choice, we may map K1 to K2 and K2 to K1. So this is a typical situation with graph-directed systems. Maybe to understand graph-directed system, you can at first you can construct the following very simple example. Consider a square and a triangle. Yes? And let us suppose that this square consists of two squares and two triangles, right? And suppose this triangle consists of one square and also two triangles, maybe this way. You see? Mm-hmm. Is it possible to construct such a system? Is it possible to construct such a system? Of course it is possible, it is easy. So suppose this is 0, 0, this is 1, 1, this is 1/2, 0, this is 1, 0, this is 0, 0, 1/2, 0, 1, 0, right? And I need to write the maps, yes, which send first set to the first set in these three different ways, yes, and second set to the first set and second set in these different ways. So, and I write K1 is equal to, I will write it just as a comment in IFS style, yes? So it is 1 divided by 2 multiplied by K1, yes? And also union, this will be 1/2, 1/2. But since we have 1/2 both times, then it will be better to write this way. 1/2 multiplied by 2 copies. First is identical, and second is shifted by 1, 1. Right? Yes? Multiplied by K1. Please repeat your question.
Okay, sir.
Yes. So if I am wrong, please prove that I am wrong, and I will ask for. Will ask to forgive me, but at that moment I am right. Therefore, no problem. And now I need to add here 2 triangles. Yes, the first triangle is this. How to put? I need to rotate this triangle 90 degrees. Clockwise, yes, and then I need to shift it to this point 0, 1, right? And it must be contracted 2 times. You see? So let us write this transformation. I shift it by 0, 1, 0, 1, yes? Then, but before that, I contract it 1/2 by 1/2, Yes, 2 times smaller. And but before that, I have to rotate it. How to rotate it clockwise? What is the matrix of clockwise rotations by 90 degrees? So if you have a vector AB, if you rotate it here, then it will be B minus A. Yes? AB goes to B minus A. AB goes to B minus A. So the first coordinate goes to minus second. It will be a matrix. A goes to A goes here and B goes there, right? This is a matrix of rotation, of clockwise rotation. Let us check. When I was child, I could not distinguish between right and left. Yes? Therefore, I need to check. Is it a right rotation or left rotation? For example, if I take 1, 0, where it goes? 0 minus 1, so it looks there. Yes? Okay, so we rotate it clockwise. Okay, clockwise rotation is 0, 1, minus 1, 0. This is the first, and this is counterclockwise rotation with the translation by with the translation by 1, 0. Okay. So I will write it not economically, but 1, 0 multiplied by 1/2, and multiplied by 0 minus 1, 1, 0. Yes, this is a counterclockwise rotation, and this union is applied to K2. You see, and then we write K2. We need to express K2 in our terms. So it will be 1/2 multiplied by K1, right? We took K1 and shrinked it 2 times. And also we have 2 rotated triangles. Rotated, they are rotated at which angle? It is a So initially it was here, and now it became here. It's 5 pi. So what is the matrix of this rotation? So first, I need to understand what is the. It is a. If it is 1, this is 1/2, and this is square root divided. Square root divided by 2. No, square root of 2 divided by 4. Square root of 2 divided by 4, right? Square root of 2 divided by 4, it works for those both two. And 1 second. First, we need to find coordinates of these 2 points. These coordinates of these 2 points are 1/4, and it will be 3/4. Yes. So I write the coordinates of the vertex: 1/4, 3/4. Yes. Then I multiply it by a rotation by how much? 1, 2, 3, 4, 5 pi divided by 4. No, no. Oh no. How much, what is this angle? 3 pi divided by 4, right? 3 pi divided by 4. 3 pi divided by 4. And also I add a translation to this point. And this will be 3 divided by 4, 1 divided by 4. So it will be 3 divided by 4, 1 divided by 4. If somebody can and multiplied by rotation, which is this rotation? Minus 3 divided by minus rotation by minus 3 pi divided by 4. Am I right? Minus 3 pi divided by 4. And all these two components are shrinked square root of 2 by square root of 2 divided by 4. Square root. So it may be written as 2 to the power minus 1.5. Yes? And this is K1, and here it will be, this is applied to K2. Do you see what is written on this part of the blackboard? Is it visible? It's okay? Okay. So now you will construct an attractor of a graph-directed system. Usually, construction is being blocked by some mistakes. On that way, you need to eliminate the mistakes, and then you will get the success. I think that we need to make a break. Yes, and after break, I will continue this explanation of graph-directed systems, because I need to explain multi-zippers.